Okay, hi everyone. Welcome to this retronet call in which we will be talking about E1 and more specifically the analog side of it. So, if you don't know what E1 is, I suggest you watch a couple of the previous retronet call. There was one by Harald that was presenting E1 and various other TDM protocols, and then there was another one in which I presented the ICE E1 USB, which is um, a USB to E1 interface that we developed and that will be featured in this talk. So why would you be interested in the electrical level of E1? Well, for me, an aspect of it was purely the curiosity, knowing what the spec says and things like that, and especially what are the potential implication when you choose to deviate from those specifications. Another motivation was to validate the ICE1 USB fee. So this E1 interface that I developed doesn't use an LIU. So LIU stands for Line Interface Unit, and it's a chip whose dedicated purpose is all the electrical interfacing. And because those are expensive and they tend to become hard to find nowadays, um, in the ICE1 USB, I actually didn't use one and used some analog trickery. And so I wanted to test, okay, I know that it works, it interfaces just fine with other E1 equipment, but how close am I to the real specification? I wanted to test that, and also is there some ways to improve it? And finally, is to be able to remove the LIU in more application because, as I said, they're really becoming hard to find. One of such application is the A1 tracer, which is like a passive tap for E1 that still relies on an LIU for the interfacing to be sure uh, to be a capture very weak signals because during the passive tapping process, the signal gets attenuated a lot, and LIU usually have a function for amplification and stuff like that. So, can we do without it? So, here is the outline of the talk. I'll start by reviewing the specification so that we know what we're talking about. I will go through the methods and tools that I plan on using to test compliance to those specifications. I will do a few sanity checks on those tools to actually check that they behave as I expect. And finally, I will actually run some devices through those tests to check for compliance. And we'll look at the results and you know what can we do in the future and what we'll talk about in part two of this talk. So the specification, what they say is that in general, E1 is a 120 ohm nominal impedance system. There is a 75 ohm variant. But we're not going to be talking about this here. What the variant that we use all the time here is the 120 ohm over twisted pair. So like basically, normal UTP-5 cable or something. The signal is HDB3 encoded. Now, the only thing that's relevant for us here is that there is three electrical states. So either there is an absence of voltage, like 0 volt, the two wires of the pairs are at the same electrical level, or there is a positive pulse or a negative pulse, and that pulse should nominally be 3 volts into a 120 ohm resistive load. There's also obviously some timing specification in the specs. The signal is 2048 kilobits, and there is an accuracy of 50 ppm. We're not going to be analyzing this here, mostly because from an accuracy standpoint, because the ICE1 USB was designed to be a clock master and a clock source for GSM BTS, we actually aimed for something that is much, much more precise than 50 ppm, and we support GPS lock. And so we have like sub ppm accuracy. So this is not something we're gonna test here. And from a jitter standpoint, we're also much better than required because the specifications are not especially tight from the standpoint of jitter. And the VCXO we use as a native jitter that is orders of magnitude lower than the specification. And architecturally, the E1 signal that we're sending out is basically a direct divide of that VCXO, where we will be adding like very little jitter. So that's not really much of a concern here. So if you have no idea what an E1 signal looks like, well, this is an example that I captured from TE110P card. And you can clearly see that you have positive going pulse and negative going pulse, or no pulse at all. The fact that in the middle you only have like a positive pulse is just an artifact of the fact that, that's what I was triggering on, but you can have positive pulse and negative pulse. So what do the specs say? We'll start by looking at the transmitter. And there is two things that are specified for a transmitter, is that its nominal source impedance should be 120 ohm, and that's specified in the form of a return loss. So basically, if you're transmitting into a 120 ohm resistive load, which is like the perfect load for the system, you should have a return loss that is lower than 6 dB between 51 kilohertz and 102 kilohertz, and lower than 8 dB between 102 and 3072 kilohertz. No, that return loss is actually not that strict. If you look at, what kind of source impedance would meet those requirements, anything between 55 and 280 ohm would actually meet them, assuming everything else is ideal, of course, which won't be the case. But it's just to say that this is not an especially hard to meet specification, at least at first glance. The other thing that is specified in the specs is compliance to a specific pulse shape, and that is what is described here. So you can see that your signal should basically be in the white area and not in the barred area. And so you must transmit a 3-volt pulse into 120 ohm, and it has to, have this amount of overshoot, or cannot overshoot higher or cannot undershoot lower, that kind of things. It has to have this width and, fit basically in that mask. Something to note here is that a 3-volt pulse into 120 ohm is actually quite a bit of power. It's 75 milliwatts. And because you nominally need to have a source impedance of 120 ohm, that means that you will be basically burning another 75 milliwatts into the source termination. That's 150 milliwatts in total. That's quite a bit of power. And we'll see that in the ICE1 USB case, it's actually something that caused the non-compliance. If we move on to the receivers, what is specified is that it must present load impedance of 120 ohm again. The return loss requirements are definitely stricter than for the transmitter, because here we must meet, minus 12 or down to minus 18 dB return loss between 102 and 2048 kilohertz. There is another specification for the receiver, and that's noise and crosstalk immunity. So basically, there's a whole paragraph in the specification that describe some tests that you must perform, where basically you take normal E1 signal, you add to it an interferer signal that has an SNR of 18 dB. So the interferer is like 18 dB lower in power compared to your wanted signal. That interferer must be a valid E1 signal, like a valid HDB3 encoded signal that you must feed with PRNG, basically, for the data that's actually encoded. It must be non-synchronous with your main signal, so that, basically the pulses drift compared to each other. They're not perfectly aligned, that kind of thing. And the total combined signal can be attenuated from 0 to 6 dB. And in all those cases, the main signal must be received without errors. So that's something that we should be testing for sure. Unfortunately, although they describe that magical combining, they don't really provide any example circuit on how to do it. Yeah, so that's something we'll have to look into. So as for the methods that we'll use for testing different things, well, the return loss measurement, that's, the high level way of doing it is that you have an ideal source that you're feeding into a VSWR bridge, which is like a return loss bridge. And that bridge will send the signal from the source into the DUT. The reflection from the DUT will be directed toward a power meter, and then you can look at the power that you receive in your power meter compared to the power that you injected, and you basically have what's called the return loss. And then you do that sweeping the various frequency range, and you get your data. Now, for when you when you're testing a receiver, that's easy. You just plug that into the receiver port. If you want to test the return loss of a transmitter, uh, you actually do send the signal into the transmitter port, into the output. Basically, you're feeding your out signal into the output. The sort of complicated part is that your transmitter must be powered, because most transmitter will present different electrical characteristics if they're not powered. But it must not be transmitting any kind of pulses, because else it's gonna mess with your measurements. So it must be transmitting like a zero pulse. We'll explore two methods. One is using an off-the-shelf vector network analyzer, and the other is a sort of a homebrew approach to the problem, and we will be comparing both. So this is the off-the-shelf network analyzer that I, decided to use. Why would you go with off-the-shelf network analyzer? Well, they're kind of specifically designed for that kind of measurement, so they're kind of a perfect fit. Of course, they tend to be expensive and hard to find. There is like Nano VNA, which is more affordable, but I don't have one of those. Here, I will be using the DPS KC 901V. It's not a great network analyzer by any mean, but it's definitely decent. It covers a range of frequency which is way higher than what we need, but it does go down to like 10 kilohertz or something. So it definitely covers the range of frequency from 50 kilohertz to like about 3.2 megahertz that we need to concern ourselves with. It has a decent dynamic range, not perfect, but not bad. And also, I mean, it's what I happen to have around, so that's why I used it. Now, small problem is that most off-the-shelf network analyzer are designed for use in 50 ohm systems, which is not the same as 120 ohm systems. So if you try to plug a 120 ohm load, it will measure a very high return loss because it's not designed for it. So we need some kind of external matching for that. And the solution is what's called a minimum loss pad. And that's gonna convert from one impedance to the other. So it looks like this. It's basically three resistors, and you can even do it with two. Here I did it with three just to try to be symmetrical on the balanced port side, but it doesn't actually change anything. And on one side you will see a 50 ohm, and on the other side you will see 120 ohm. Now the downside of this is that it adds loss. It's kind of in the name. It's a minimum loss, but it's still loss. Here in this case, for these particular values of resistors and going from 50 to 120, it will add approximately 8.75 dB of loss. And that's both in the forward and reverse direction. So the total loss is like 17.5 dB, and that's 17.5 dB of your network analyzer dynamic range that just heated lost in the matching, and that you can't get back. So thankfully, we're not trying to measure very low return losses. We saw in the spec like the lower was only minus 18. So even with 17.5 and then like let's say 10 dB of margin or something, we still only need about 50 dB of dynamic range out of our network analyzer, but it's something definitely to consider. Of course, this matching will not be perfect because of those resistors are not perfect, and I couldn't find like it's not 65, it's 65 dot something that you need, but it will be good enough at least that the VNA calibration will compensate for any non-idealities of your matching in this case, because you basically perform the calibration with the minimum loss pad, and then you perform the short, the open, and the load on the 120 ohm side. That's what the setup looks like. Just the analyzer connected through SMA to the minimum loss pad, and then I have like a very tiny adapter which goes from the LG45 port that typically E1 equipment has to like the pin header that I have in my adapter and in the other various test equipment. So the other option is to just build my own homebrew network analyzer, designed from the ground up for using Z0, at 120 ohm. Because the frequency range that we're working with is fairly limited, we only need to test between 50 kilohertz and like a 3.072 megahertz or something. It's not actually that hard. And there's three main parts to it. As you saw in the beginning, is we need a return loss bridge, we need the signal source, and we need something to receive and measure the return power. Now, I will use a classic oscilloscope and a classic, lab signal generator controlled to the network for the source and the data acquisition side with some adaptation. So the bridge that I decided to use is based on this paper, which is like a fairly old paper called Simple SMT Circuit Mimics Ultra Broadband Coupler. And it's actually a very, very nice circuit. And as far as I know, like modern, network analyzer use a circuit that's derived from this. Like in that paper, the author goes through the basic variant that I'm using, which just consists of some resistors, and then derives more complex variant of the circuit. Because the main problem of the circuit as it is here is that the source, the DUT, and the reverse power ports, they kind of must be floating with regard to each other, because like they cannot all have the same ground, for instance. And so when you're using this like in a circuit or something like that, it can be very annoying. And so the author derived some more complex version of this using various balloons and stuff like that to lift that requirement. In my case, that's not necessary. I can live with that limitation. And so that means that the bridge is literally just 4 120 ohm resistors, no balloons or anything like that. And the parasitics of just using, SMDs 0603 are the capacitance or their, inductance and that kind of stuff are gonna be fairly negligible at the 3 megahertz or so that we're testing at. Now the downside also of this system, because I used all the resistor of the same value, is that it's fairly high loss. So I don't remember the exact loss, but I think it might be like it's either 6 or 12 dB of loss between what I inject in the source and what goes into the DUT. So it's fairly significant, but I can definitely live with it. Again, because the return loss we're looking for are only minus 18 dB or so, which mean that we don't need that much dynamic range. The other block we need is a source. So the goal here is to convert from the output of a signal generator, lab signal generator, which is typically going to be 50 ohm, and to convert it to 120 ohm. I mean, I could obviously have used the same minimum loss pad, but first I didn't want to pay the price of the loss of the matching, and I also wanted isolation. So I wanted the signal generator ground not to be tied to any particular point in my test circuit. So I added ADT1-60 plus transformer, which is good down to 30 kilohertz up to several megahertz. That's not a problem. And I'm also using an amplifier, an active amplifier, an 8132. That's gonna compensate for the matching loss, and it will provide a 3-to-1 voltage gain we look at what it looks like here, it's fairly simple. You just have the input going into the transformer. Then this is directly terminated to 50 ohm. Um, the resistor is actually 51 ohm, but when you combine it with the input impedance of the 8132 through those two 1K1, it actually brings it to like 49.9 something or something. And yeah, just a simple differential gain circuit with an output impedance of 103 ohm, and this is the actual PC board. This whole down part here is the power supply because it takes like a symmetric power supply, and that power supply is also isolated. So in the resulting circuit, the input is isolated from the output and from the power input, and the output is isolated also from the power input. So it's all floating, no common reference needed. The other side of the return loss measurement is the receiver. And so the goal here is just to probe a signal and send it to the scope. I could have used, you know, simple scope probe, but simple scope probe, you know, are typically 10 to 1 to have the bandwidth requirements. And the other thing is that that would actually come on the ground of my inputs, which is not ideal. I wanted them to be differential probes, basically. So it's basically a homemade differential probe with a selectable 2 to 1 or 8 to 1 voltage gain. And it has a 50 ohm output, but I don't actually terminate it to 50 ohm in the scope. That's not required. But the source impedance of 50 ohm still helps prevent multiple reflection in the cables. So this is the receiver actually has two channels, one here and one here. This is the actual bridge implemented, where you can see like the 4 resistors here, and this is again the power supply. And then there is various jumpers to select what you want to probe, and a bonus bodge wire because I probed the wrong resistor. Anyway, so that's what it looks like. Just 8131. It's basically a differential receiver. There's nothing special, and the jumper to select the gain actually just bypasses one of the feedback resistors. So as I mentioned, the power supply in both circuit is isolated. I wanted to do that again to try to have everything as much floating as possible. And because also I wanted each circuit to only have like a single 5-volt input, but I needed, sometimes plus or minus 12 volt or plus and minus 5 volt for the op amps. I decided to use an off-the-shelf DC-DC converter from the TBA2 series, and then some filtering, and then follow that by a LT32 dual linear regulator, which has the positive and negative side. It turned out to be not a great decision because the result is actually very noisy. There is lots of spikes everywhere, even through the regulators and inductors and stuff like that. That was a bit surprising, but yeah, I guess either I made it too compact, or there's some coupling somewhere or something. But anyway, thankfully, it doesn't actually affect the measurement that much because since the noise of the isolated DC-DC converter is completely uncorrelated to the source signal, I can actually just filter whatever I receive to what I expect, just to keep that. And here I do that just using scope averaging. And if we look at the result, so that this is the schematic. You have the input with some common mode filtering, the converter, some more common mode filtering, and then some large capacitance, the linear regulators, and then some output capacitance, stuff like that, and then directly the symmetric volt output. And if we look at the output, this is what it looks like. That's not the output of the power rail, to be clear. It's the above signal attenuated a lot to a very small sign, and then just looking at what the receiver sees, basically. And we can see that periodically we get a lot of spikes that are completely uncorrelated with the input signal. But if we turn here like a 32 averaging, those spikes basically disappear, and we have a pretty clean sign that we capture, and for which we can definitely determine the amplitude and phase compared to our reference sign without too much issues. That's what the setup looks like. The power coming from a classic lab power supply going into the both modules. The output of the transmitter goes into the drive side of the VSWR bridge, and then the DUT side is connected to our device on the test. And here, this comes from the lab signal generators, and this goes to channel 1 and channel 3 of my oscilloscope. One of them is going to be the reference signal, which just serves as a phase reference. The amplitude is through calibration, and the second one is return signal, basically. Sorry. So that's what the data acquisition looks like. In my case, I use the Negeland 3000X. The signal generator is just a sine source that I vary between 30 kilohertz and 3.2 megahertz. I don't go lower than 30 kilohertz because the ADT transformer isn't rated for lower than 30 kilohertz, and it really starts to distort the signal if you go lower than that. But it doesn't matter because in any way, our specification only call for 50 kilohertz, so that's fine. The scope as the reference and return signal. It's all controlled from a Python script. The script performs the sweep and records the phase and amplitude results directly from the scope measurement function, and they're recorded as S1P. It's like a S1 parameter file. Those data are loaded into the scikit rf Python package, and that package is pretty neat because first it can handle all the plotting, loading the data file and all the plotting, and it also handles the short open load calibration math. So I can do a sweep for a short, a sweep for an open, a sweep for an ideal 128 ohm, feed that, and it will actually compute calibration coefficients to try to remove the imperfection from the system. There is a small bug that took me like a good half a day to debug, where if your impedance is different than 50 ohm, the calibration math actually doesn't work. And so I had to fix that before I could actually use it for this. So these are my short, open, and load standards. It's really just a pin header with a solder bridge, nothing, or 120 ohm like precision resistor soldered across the pin, and it works decently well. That's what I use to calibrate both my homebrew network analyzer, but also the off-the-shelf network analyzer. Something else that we must test, according to the spec, is the noise and interference immunity of a receiver, and for that we need to combine two E1 signals. And so, because no example circuit is provided, I kind of needed to try to design one. The goal is to have two inputs that present a 120 ohm load to their driver, an output that has a 120 ohm characteristic impedance. One of the paths must not have any attenuation, and the other must have 18 dB attenuation. Ideally, I should have some kind of minor adjustability of those ratios, simply because most likely they won't be perfect, right? So it's nice to have some way to tweak it slightly, and also it'd be nice to be able to test it in more difficult conditions, like instead of testing SNR of 18 dB, we can test 17 or 16 or something like that to make sure, okay, like if it still works at 16, we can be fairly confident that we are meeting the specification. We also need to be able to attenuate the output by anywhere. Technically, it should be anywhere between 0 and 6, but if we have 0, 3, and 6, that's sufficient for us to test to be able to simulate cable loss. Now, that combiner, adding two signals with one of the paths being 0 dB while still presenting a 120 ohm impedance in all the ports, you just cannot do that passively. That's just not happening. you need an active component somewhere. So I decided to reuse the 808132 differential amplifier. Basically, I take all the input signals, terminate them to 120 ohm, and then try to combine them using a high impedance passive network, like a passive resistor adder, basically, amplify the result and drive the output with 120 ohm in series. Unfortunately, that didn't exactly work according to plan, and some of the parasitics got in the way, and they actually didn't get in the way in the way that I expected they would. If we look at the schematic, this is what it looks like. So you have the two inputs. Each of them is terminated, and then you have three resistors that you can select. If you want to tweak slightly the combining ratio, and those are fairly high impedance. Here 5 kilo ohm, but like especially for the 18 dB attenuated pass, we're talking like 50 kilo ohms and stuff like that. And then here you have the resistor that you can choose for the feedback that will dictate the output attenuation, basically. And honestly, I thought that at the frequencies that we were looking at, the parasitics wouldn't be an issue, but I forgot two things. Is that first, yes, when you're talking about the 120 ohm, like the few picofarad of parasitic of the 808132 don't matter, right? But when you're talking about 30, 40 kilo ohm multiplied by 2, because like it's in both paths, 40 kilo ohms and a few picofarad, that starts to be definitely a low pass for high frequencies. And the other thing is that here we're not limited to the 3.23 megahertz of the spec. We actually need to go to at least 10, 20 megahertz of bandwidth, because we don't want to change the shape of the pulse. And the shape of the pulse has harmonics way higher than the bitrate of 2.048. So yeah, I think like a flat response up to 20 megahertz would definitely be a design goal, and this definitely does not meet it. So this definitely will need a redesign. But I expected all of this to basically be a low pass, simply because of the input capacitance of the 8132. But we'll see that's not the case at all, and I haven't fully explained that yet, actually. This is what it looks like. I have an E1 test board that has a bunch of test circuits. One of them is that combiner, and so you can see here. This is just generating the reference voltage for the mid rail, to have like the symmetric power supply for the op amp. This is the input one with the termination in the center, and then the three resistors on each side to select which combining ratio you want, and the jumpers. You have the same thing for the input one. Then you have the actual op amp and this, and then you have the output. It's going through a one-to-one pulse transformer, specifically designed for E1. This actually uses the upper side of this transformer, and this one is a one-to-one ratio. The lower part is used for another test circuit. Now that we have our plan for testing and the tools that we want to use, what is the we should perform some sanity check on them to check that they actually behave as we want. So the first thing I did was test the frequency response of the TX and AX module, because basically the goal was to have more or less flat frequency response in the bandwidth of interest from like 50 kilohertz to 3.072 megahertz, which is the area that we need to test. It doesn't need to be perfect, because a lot of it will be dealt with by calibration, so that's fine. But it also cannot be terrible, because this might introduce distortion or reduce or dynamic range, or overdrive something, that kind of things. So the test for the transmitter is simply take the signal from the signal generator, put it through the transmit modules, terminate the output of the transmit module into a 120 ohm load, and look at it in a scope probe. Now what we expect is because it has a voltage gain of 3 to 1, but with 120, you basically lose half of the voltage because of the termination, right? You have a 120 ohm output impedance, so it forms a voltage divider. So the total gain is voltage gain is 1.5, and a voltage gain of 1.5 is basically 3.5 dB. We want to test the frequency response of the receiver, and it's basically kind of the same thing, is that we take the signal from a signal generator. Here we send it through a 50 ohm termination, and we probe the output of, we probe the terminals of that 50 ohm termination with our receiver module. Our receiver module has a high input impedance, so it won't affect the termination. And we feed that through our scope input. Now, what we expect, because the voltage gain is either 2 to 1 or 8 to 1, is basically a gain of 6 dB or 18 dB. And these are the results. The gray line are, so the plot is logarithmic, both magnitude because it's in dB, and the frequency plot here is logarithmic at all. The two gray line represent 50 kilohertz and 3.2 megahertz, which is like the bounds that I was really testing in. And you have every time, so for, if you look at the transmit, the blue line there is the transmit. The dashed blue line, the dashed line is the theoretical 3.5 dB, and we can see that we are sticking to it very well. Same thing for the Eric's low gain. We have slightly more gain, but it's very flat. And same thing for the receive high gain. It's also very flat and very close to the theoretical value of 18 dB. So really no problem on that side. That worked very well. But we can see that on the Eric's high gain, there is a frequency roll-off at higher frequency for sure. Like when we get to like 10 megahertz, so a 3 dB point would be 15 dB, which would be around here, which is around 15 megahertz or so. But it's way above what we're testing, so it's fine. Another sanity check that I wanted to do is basically test the entire concept of both the homebrew and the minimal loss pad, because I had never used the minimal loss pad before, so I wasn't sure if it was gonna do what it said it would. And so I decided to basically do a full test, measuring the return loss of two DUTs and compare them, once with the OTS, one with the homebrew. And the two DUTs that I checked were a pure 51 resistor, the precision 51 ohm resistor. The theoretical return loss for it should be 7.88 dB. That's what we should see. And it should also be fairly flat because it's a resistor. So between 50 kilohertz and 3.2 megahertz, it won't have much of a parasitics that would affect its frequency response really. And the other is to look at the 120 ohm resistor, but through E1 magnetics and an RG45 connectors. Again, I expect a very good match here, because it's a 120 ohm resistor at the end, so it should be good. There should be some influence of the E1 magnetics because transformers, then they have a minimal frequencies. So at low frequency, it will definitely degrade, but it should still stay very good. And this is what I measured for the 51 ohm resistor. And in the dashed blue line in the middle here is the theoretical value. In orange is the result of my homebrew, and the blue line is the commercial off-the-shelf network analyzer with the minimal loss pad. And you can see that first they are close to each other, and they're also close to the theoretical value, so that's really good. Now, don't pay too much attention to the fact that the commercial network analyzer seems to be more noisy and stuff like that, and it might be that it is, but it also has many more points. I think that the trace that is generating has 900 points, while for my homebrew one I was only capturing like 100 points. So yeah, but the results are pretty good, because if you look at the scale here, we're looking at 2 dB, right? So we are very, very, very close to what we're looking for. And this is the measure for the what I call the mag load, which is basically the 120 ohm resistor through the E1 magnetics. And again, it is a very good match. Like we're, you know, better than minus 25 um, dB return loss, which is definitely not bad. Uh, and the shape of both does stick. Now, the KC Nano 1V reads slightly higher, and it's sort of a constant in every measurement. I'm not entirely sure why. It's usually only like 1 dB or so, which is um, not something I'm concerning myself too much with, because like if I'm looking for compliance and stuff like that, I definitely want it to be like way better than the spec says. So like, I have a few dB of margin rather than just cutting it super close. So I'm not too concerned about the difference. It'd be nice to explain it and do more tests, try to explain it, but I just really didn't have the time to um, do more than what I did. Now we come to the sanity check of the combiner. So basically testing the frequency response of the combiner itself. Again, I'm using a lab signal generator that's network control and sweeping, um, going through the transmit module that was designed. As we saw, the transmit module actually had a pretty flat frequency response up to 20 megahertz. That one is not a problem or affecting the frequency response too much. And it will also be calibrated out, kind of. And then we take that, we input it to an input of the combiner, and then we look at the output of the combiner with a scope probe and look at the amplitude and basically plot the frequency response. So this is the frequency response for the final gain adjust. I kind of normalized it. I took 0 dB as the reference to kind of calibrate everything factor out, and we can see that at the beginning it is kind of flat and it is -3 and -6, but in the higher frequency, the attenuation is not 3 dB at all. Like, it's definitely peaking, which is not what I expected. I didn't expect peaking at high frequency. The more interesting plot is when we look at the frequency response of input 0 to the output and output 1. And we can see again, here it's fairly flat and fairly close to the theoretical values. But at high frequency, we've got peaking. And here it's not too bad in the sense that if we look at 20 megahertz, we have maybe 1 dB. So it's not terrible. It's maybe 1.5 dB. It's definitely not ideal because it will show up as overshoot and undershoot, which we definitely don't want. But if we look at the input 0, which is the pass that had the higher impedance through the combining network, and that frequency response is just not usable, like, at all. You can see that compared to, we're not too far off from the theoretical values, and the green is a little low here, but it's not terrible. It's just due to the resistor values. Like, you compute theoretical values, but then you actually have to buy real resistors that you can buy and are in stock, and you can't always buy the exact good values. So that's why this one is slightly more off than the other. But the peaking here at high frequency is just unusable. Like, if you look even already at 3 megahertz, we're something like 2 dB above, and it's peaking at maybe like 2.5, 3 dB above what it's designed to do. That's just not usable. Yeah, like this goes to like -15, and it's lower than -18. So it's more than 3 dB. That's unusable. And I've witnessed it. Like, here you only see the frequency response plot, but when I was looking at the pulse shape before and after the combiner, I could see that the pulse was heavily deformed and had heavy over and undershoot to the point of not being recognizable as an E1 pulse anymore. So, yeah, that's not usable. I will have to identify exactly why there is peaking at high frequency. I suspect there is some parasitic capacitance in the feedback network or something. Um, so the next step for this is basically trying to reproduce this in spice simulation, trying to introduce parasitics of various value to try to obtain the same kind of frequency response that I observe, and then try some changes in simulations, validate that on hardware. I've definitely several ways that I could go. Some of them actually reuse the exact same PCB that I already have, just changing some resistor because ideally I want to avoid having to respin a board. I might have to, but if I can avoid it and just change some resistor, I will definitely go for that. So that will definitely be for part 2 of this talk. So finally, after all of these talks of describing the specification and the testing method that I'm going to use, we can finally move on to the actual results, at least those that I have. So the tests I performed are receiver return loss, transmitter return loss, and transmitter pulse shape. There's obviously no receiver noise immunity testing, simply because the combiner doesn't work to it's not usable, so I can't use it for testing or anything. I tested this on 3 DUTs. Even though I'm really only interested in the ICE1 USB results, I thought that the other two would be interesting, even only as kind of reference points. One of them is a TE 110p clone. Um, Another is an LIU, the IDT 82V2081. That's the LIU that we used on the Osmo X1 Xever board that you can find in the E1 hardware repo. It's like a small dev board that we used for testing this LIU. So, receiver return loss. This is the ICE1 USB schematic, so we can look at what do we expect and see if the actual testing matches our expectation. The E1 signal comes from here, from the this is the NTT kind of selection jumper block. So the E1 signal and basically end up here. This is the classic E1 um, magnetics. This is just ESD protection. It has very low capacitance and will not play a role here in normal with normal signals. This is just a biasing circuit that we introduce in the center tab so that we have like an electrical level reference for those two lines. So the first thing that enter into account is this, which is the 120 ohm termination. So that should pretty much be ideal. And then this is fed into this, which is like the analog receiving circuit. But that analog receiving circuit, if we look at it, like the capacitors at the frequency of interest, they're just going to appear as shorts. So that's fine from a small signal point of view, I mean, from an impedance point of view. And then it's all terminated to 10K resistor, which are fairly high impedance compared to the 120 ohm from here. So they will not really play a role. We could they will play a tiny bit role because there's 4 of them in parallel, so it's going to be like 2.5K. So it will influence the impedance that's seen here, and so we could possibly have used maybe 130 ohm here or something to have a better match. But still, I expect something a very good match. And these are the results for the other DUTs. We have the here in blue and orange, it's the LIU, the IDT 82V2081. As you can see, we have the same shape, but slightly offset. It might actually be, from looking at this plot, it might actually be offset in frequency, actually. And maybe that's why I was seeing like a different response from the homebrew versus off the shelf. I'm not sure. But anyway, it's very well matched. Like the black line here in dashed is the specification. We must be under this. So the LIU is very, very well matched. The T110P, on the other hand, we can see it actually doesn't meet the specification. And I've rechecked this like several times and redid the measurement and redid the calibration to make sure. And no, like at higher frequency, this board doesn't actually match the specification. The return loss is higher than the spec, what the spec says they should be. So that was definitely surprising. No, it is a clone card. It's not an official Digium card or anything. So it's like a cheap clone for China. So maybe they used the wrong value, or maybe something is configured badly. I have no idea, but that's the case. Um, Note that the card was powered up and configured as E1, because a bunch of these chips actually have, it can work in E1 and T1 mode, and they will actually vary their input impedance depending on the mode that is currently selected. So the IDT, for instance, was correctly configured to be in E1 mode. You can clearly see it if you configure it for like T1 mode, like the return loss will jump, you know, jump high because the match is terrible at that point. And if we look at the iPhone USB, I actually did 4 tests. Tested both ports, port 0 and port 1. They should be the same, but it was to have like 2 measurements, and I tested them both with the off-the-shelf network analyzer and my homebrew solution, and we can see that both solutions pretty much agree, and that we have a lot of margin in the match. Like it does degrade at lower frequency. That's because of the magnetics basically that don't work as well in the low frequency. But even there, like we still have, a good 8 or 10 dB of margin, which is pretty massive. So yeah, nice one USB receiver return loss, no problems. Yeah, that's basically the explanation of the schematic and the results. Now the transmitter return loss. So this is the transmit circuit for the ICE1 USB. It's basically, these are directly from the FPGA IOs, and they drive the transformer directly through 27 ohm resistors. Now, the output impedance of the FPGA IO, the classic CMOS IO, and I actually did characterize, actually I think I have that, yes. I did characterize the ICE40 UP5K drivers. You can see the IV curve in sync and source mode of the FPGA IO. And so if you look at the derivative of these curves, that will actually give you the impedance. And if you look at the derivative at the operating point that we use in the ICE1 USB, it's going to be basically 24 ohms. That's the output impedance of each driver. So that means that on this side of the transformer, our impedance is going to be 24 ohms plus 27 plus 27 plus 24. And that is going to be 102 ohm impedance. But of course, we have a transformer here, and that transformer is a 1 to 2. It's basically a voltage doubler transformer, and that's going to modify our drive impedance. And it's going to modify it by the square of the ratio, by 4, which means that our drive impedance on this side of the transformer is actually going to be 102 multiplied by 4. It's going to be 408 ohm drive impedance. And a 408 ohm drive impedance is not even close to 120 ohm that we should be achieving. So our return loss is actually not going to be that great. I don't expect it to be that great. I think the theoretical value that we should be getting is something like 5.5 dB or something. I don't remember exactly. I have it on the next slide, the theoretical value, but yeah. The drive circuit as it is, I don't expect a good match. So this is the other DUT that I tested. I did test the LIU itself, and there's actually a bunch of weirdness in these measurements, so take them with a grain of salt, because for the IDT 82V2081, the measurement between my homebrew analyzer and the off-the-shelf one actually have quite a bit of difference, and I did check them several times, but when I looked at the time domain of the signals, I saw something very weird. Is that I would input a sign at one frequency for measurement purposes, like the excitation signal, and the return signal would basically be not looking like the original sign, like it would be altered somehow. And I think that might be because the drive circuit of the IDT 2881 has dynamically variable impedance, because it does support E1 and T1 and stuff like that. So I think it has some active components to it. And so I think it just doesn't like being driven in reverse like that. I think that's probably why I'm seeing some weirdness. But anyway, it does seem to meet the requirement anyway. Uh, i- some more investigation could be done, but again, I was limited by in time. Um, for the tier 110p, there is only the homebrew measurement, and even then, I wouldn't give too much credit to it, simply because, for the LIU, I have somewhat control to it, and so I could actually, power up the transmitter but transmit zero all the time, disable the LGBT encoding, and just transmit zero all the time, basically. For the tier 110p, I just couldn't do that. Like if I power and configure the card with Daddy, the card is transmitting an E1 signal. There's no way I can stop that, which is not good because obviously, if it's transmitting an E1 signal, it's interfering with the measurement, and the network analyzer, like the commercial of the shelf network analyzer, couldn't make any sense of the results. Like I had a positive return loss, which makes no sense. Um, with the homebrew system, because I was relying on scope averaging, I could actually increase the number of average, and because the transmit signal by the card is independent of my excitation signal, the averaging would actually basically end up suppressing it. So that's why I got some measurement that looks valid. I don't know how good it is or not. In any case, it's compliant, barely, but it is compliant. Um, but yeah, it wasn't a great test. I did test the ICE1 USB and again all the ports. And as you can see, we are way above the specification, which is sort of expected. Like the specification says we need, I think -6 and then -8 at higher frequency. And basically everywhere we're like -5.5 or something, which is, yeah. So the theoretical return loss for the 408 ohm drive impedance that we end up with is 5.26, and I measured 5.6 dB. So there is a good match between the theoretical value and what we're actually measuring. That's the good news. The bad news is that we're nowhere even close to what we should be according to the spec, right? Um, so yeah, definitely some improvement to do there. Now we're gonna look at the transmitter pulse shape. So back to the ICE1 USB schematic that we looked at before. We know that we do have a 1.2 volt transformer, and that was there in place to try to basically get a 3 volt pulse, because we need a 3 volt pulse in one direction and a 3 volt pulse in another direction. Uh, we lose half the voltage because of if we had a perfect 120 ohm drive impedance and a perfect 120 ohm receiver impedance, we need to send a 6 volt pulse so that the receiver gets a 3 volt pulse, right? We can't generate a 6 volt pulse using a 3.3 volt IO unless we use a transformer to boost the voltage. So that's kind of why the transformer was originally there. Unfortunately, it didn't work out, as we will see, because if we do all the math, for drive impedance and the receive impedance and what things end up being, the theory says that we should get a pulse at the output, which is basically 1.5 volt instead of the 3 volt that we should have. And that's simply because, as I said, to send 3 volt pulse into 120 ohm with a 120 ohm source impedance, it would take 150 milliwatts, and that's a lot to ask of the FPGA by itself. They're just not powerful enough to drive that to that level. Um, so we could actually suppress those 27 ohm resistors, and it would actually improve the pulse. It would be higher. I don't think it would meet 3 volt, but it would be higher. But it would stress the FPGA quite a bit, and I was not confident to ship um, devices that would stress the IO that much, because I would need to do some long-term survivability, like, will the IO actually survive, stuff like that, because as it is, even in that circuit, we're already driving them beyond the spec, but we're driving them to something that I'm still comfortable with because it's just slightly above the spec. It's not terrible, but trying to get like 50 milliamp out of the IO would just be insane. Anyway, this is the pulse shape from the tier 110p clone. It looks pretty good. It's definitely like 3 volt. When it flattens out, it achieves like 3 volt perfectly. It has a tiny bit of jitter. I'm not sure why. It might be because the card was free running. It was not connected to something, so maybe it was searching for a clock source or something, trying to log to it or something. So there's a tiny bit of jitter, but not too much. Nothing bad. It does not meet the mask, I think, because there's a tiny bit of overshoot here that goes above, but it's really not that bad. Like it's I would consider that definitely pretty good. If we look at the IDT82V81 LIU, uh, there the pulse is just, I mean, it's almost perfect. Like it's really nice. It has the 3 volt amplitude, like exactly. The only thing that you can see is that there is a tiny bit of ripple. Like you can see here, here, and here, and here in the middle, and here in the middle. It's like a tiny bit of noise that's added. And given given the frequency at which it happens, I think it's actually noise leaking from the clock source, because my guess is that we have like the rising and the falling edge of the clock, the 2.048 megahertz reference clock on the Osmo X1 Xevo board. That's probably leaking somewhere and generating that tiny bit of noise. That board is like a cheap 2-layer board. It wasn't, especially paid attention to things. So it's possible that some layout is not ideal and causing that. There's also no source termination on the clock, so it's definitely radiating some fast edges and stuff like that. So this could potentially be improved, but the pulse shape looks great. And this is the IS1 USB. Nowhere even close to the mask. Um, as expected, the pulse amplitude is really not good. I mean, it's basically half of what it should be. It's like 1.5 volts measured. So that's not good. It's also way wider than it should be. And I looked at the gateway source, and indeed, like for some reason, the clock pulse is width is set to like 10 out of 15 cycles. So the internal clock of the IS1 USB is 15 times the E1 clock. It's 30.72 megahertz, and the E1 clock is 2.048 megahertz. And for some reason, I drive it high for like 10 cycles. I should drive it ideally 7.5. Now 7.5 isn't ideal because it's, well, the 0.5 is hard to make. Hard being relative, because I could use the DDR output to actually make it 7.5, and I think that's what I will actually end up doing is to make it perfect width, because that I can correct just with a gateway change. For the pulse height, I've got some circuits that I think could improve it. Um, Basically adding some more external components to try to get closer to the ideal pulse shape. That's something that I want to test for part 2 of this talk. I did some testing beginning, I began some testing, sorry. We'll see what actually happens for it. I don't pay too much attention to these things, to these artifacts. It's just because the pulse is so much off uh, compared to what it should be. The PLL that's used to draw the eye diagram here had a tiny bit of trouble locking to it, and so I had to tweak some things. But these artifacts are measurement artifacts; they're not actually in the pulse. So yeah, that's basically what I just said. The amplitude, when you do the actual math, like the final amplitude should be 1.5 volt, and that's what we see, but that's way too low. And unfortunately, just getting that from the FPGA would stress them way too much. As for the pulse width, that's correctable by Gateware. So these were the results, which is like basically the presentation of the current state. And this is what I will be working on in the future to prepare for part 2. Is the first thing is going to be fixing the combiner, so that I can do all the noise immunity testing, which I think is definitely interesting and something I want to check for the IS1 USB and also for the E1 tracer and LIU replacement. Improving the IS1 USB transmit circuit, as I said, both for the width and amplitude. The gateway chance will definitely make it in the repository because it's just a firmware update. The new circuit for the pulse amplitude, I will design one and test one. Whether or not it will actually make it into future devices being produced, that remains to be seen, simply because it would imply like a revision of the board, which is costly and stuff like that. Um, and I mean the X1 USB is a relatively low volume product. There's not much commercial interest, so I don't think anyone would pay for a revision of the board, and all the tooling for that, um, because yeah, it's a fairly cramped PCB, which means that adding any circuitry will imply some decent amount of relayout and stuff like that, and retesting. And in any case, like to be clear, the pulse that it's currently transmitted, even though it's 1.5 volt only, that pulse sent into a compliant receiver should be received correctly. Like it's a compliant receiver is perfectly capable of decoding that pulse, and that was one of the main goal of the I1 USB. It's like lab testing, over like very short cable. Um, I wouldn't send it down a 1 kilometer cable, because then the receiver might not receive it. And finally, something else that I want to test is like an amplifier. So like if we passively tap the E1 pulse through an high impedance network, we get a pulse that's massively attenuated. So we need an amplifier before we can feed to a receiving circuit. And that's something I want to look at, because it implies a bunch of fun with op amps and frequency response, stuff like that. And so I really want to kind of work a bit on my analog skills, and that looks like a fun project. So I hope that you found that interesting, and that hopefully I will see you when I get to do part 2 of this talk. Here is some resources where you can find basically the project describing both the ICE1 USB, hardware, gateway, firmware, and all the the LIU test board that I use, the Osmo X1 Xever, is also in that repository, and a link to the specification. Everything that I described, the electrical interface, is ITU G703, and more specifically the section 11 that calls for like interface at 2048 kilobits E12. That's actually what we call E1, and you can actually find the PDF in the doc specification subdirectory of the Git repository that's linked above. Okay. Well, thank you everyone, and see you at the next RetroNet call. Bye.